Radiographer, and currently I'm the Associate Professor in the Faculty of Allied Science, Srihar, Chennai. So it's very important to know about hepatic iron and fat content and its grading and how to do the post-processing for the technologists, and also about MR elastography techniques, which play a major role in diagnosing and managing these diseases. So, intracellular fat accumulation is the hallmark of liver diseases, and staging the hepatic steatosis is very crucial for its management. So, if you see here the different patterns of how the fat deposits in the liver. The first image that you see here is a diffuse deposit of fat, which is the most frequently encountered pattern, with the liver totally involved in it. Whereas in this, it's just a small foci, that is a small hyperintense area that you see where an arrow mark is put in the posterior portion of the segment 4. This is the confluent foci of fat deposit, multifocal. And here, this is a T1 weighted in-phase image, and this is a T1 weighted post-phase image, wherein you see signal loss in two subcapsular lesions, that is just below the capsule. Of course, MR spectroscopy can be used for quantifying fat. It provides very precise measurement. It isn't affected by ion deposits. It gives, in fact, accurate results. And it is also very sensitive to small changes. But then, the limitations are you can only sample a very small portion and multiple measurements are needed. Also, the fat distribution is varied and hence single measurement might not be sufficient. So we need to go for a different technique. So, and when you come to T1, the spin echo images, this is a T2 weighted fast spin echo image where comparatively you can see the signal intensity of spleen more than the signal intensity of liver in a normal liver parenchyma. Whereas here, this is a fat saturated image where you're seeing the signal intensity of spleen is hyper intense compared to that of fatty liver. So we need a much more precise method. So that is why we do the Dixon technique. You guys know what is Dixon technique. So here it's based on the chemical shift between fat and water. So there is a slight chemical shift of 3 to 4 ppm between fat and water, and there is there's a 220 hertz difference in 1.5 Tesla mRNA and 440 hertz in 3 Tesla mRNA. Now this is very important. Before we go for fat quantification or iron quantification, you need to know on what strength of magnet you're working, because the thresholds and cutoff values are different. So next is, like, if you know the in-phase and a post-phase image that we routinely do, it is based on the constructive interference of fat and water when they are in phase, that is when they are within a particular voxel when fat protons and water protons are in phase, and at times in opposed by 180 degree, that is in an out of phase. So the total signal intensity when it's a fatty liver, you can see signal loss on opposed phase images. Okay, so here if you see, I put 3 sets of images. This is in a patient with normal liver parenchyma, not much of a difference between the in-phase and the post-phase. Whereas here in a fatty liver, you can see there is signal loss on a post-phase images. And similarly, in a 6th decade patient, in a male individual, you can see how much of signal loss is there seen on a post-phase image. So, how do you calculate? That is a qualitative assessment. Say you say signal intensity changes, hyperintense, hypointense, isointense, but you need to quantify. So that quantification is basically done. You draw similar sized ROI in the liver, and for a scaling basis, you also draw ROIs on the spleen, and you calculate the signal intensity based on this formula. But then, the limitation or the pitfall of this in-phase and post-phase technique is that there can be iron content in the liver which can influence the results, and elevated liver iron can actually mask or obscure the details, or it can obscure the fat detection. So we need to have a better technique. So we need a much more robust technique Then comes the ideal IQ, which is iterative decomposition of water and fat with echo asymmetry and least squares estimation. So this is the acronym in GE. When it comes to Phillips and Siemens, it is M. Dixon Quant. Okay, so this actually addresses the T1 bias, the noise bias, eddy current, and T2 star effects. Let us see how it works. For example, if you have a 2-point Dixon, you get 4 set of images. If you have 3-point Dixon, you get 6 set of images. Suppose the signal from water is A, the signal from fat is B. So you get 6 set of images, that is fat and water, that is when they are in phase. Fat minus water, water minus fat in opposite phase. Then A plus B plus A minus B, you get water only. A plus B minus A minus B, you get fat only. The 5th set of images is your proton density fat fraction, and the 6th set of images is your R2 star relaxation. We shall see one by one. So what do you mean by proton density fat fraction? So it's a fraction, right? You have a numerator, you have a denominator. So the numerator is the signals from the mobile protons in fat. The denominator is the sum of the mobile protons in fat and water. So this is the fat fraction that we are going to quantify. So this is the R2 star relaxometric image that you're seeing. That is the 6th set of image that you get. So this will be useful for quantifying ion content. Now if you see here, these are the 6 set of images that I said: in phase, opposite phase, fat only, water only, PDFF and R2 star images. So how do we do this now? Just as like any other abdomen study that you do, you could use your air coil or phase matrix coil or your surface wraparound coil. Patient lies with your hands above, fasting is necessary, and the TR and TE is, you have varied range of TEs. So the same TR is the same, whereas you have varied TEs. Now that is with 0.7 delta T. So what is delta T? It is a difference in the echo times between 2 different gradient echo which is employed in this acquisition. Now this is very important because we are going to exploit this to separate fat and water signals. So it should be appropriate. The flip panel is very less and the matrix is 160 by 160. So these are the fat fraction maps. Planning is like you focus on the liver and plan, you get fat fraction maps, and the post processing is very, very important. So when you take the first image, you should draw a 5 centimeter thick band in the center of the image which corresponds to the isocenter of the magnet. Okay, and you should place similar sized ROIs, most important, more than 2 centimeters definitely. And it should cover the liver. So one in segment 1, one in 2/3 between the second and third segment of the liver, one in the fourth segment. A more appropriate way would be placing 2 ROIs in the right lobe of the liver and 2 in the left lobe of the liver. And you also place one in the second image. You can see there's one placed in the subcutaneous fat. So there the value should be closer to 80 to 100. So this is because you need a scaling factor for comparison. Okay, so this is how your calculation has to be, and you will be taking the average. There's yet another sequence, multi-echoes point gradient echo sequence, where you have multiple echoes, and from the same image you can quantify fat and iron. So if you see here from the radiologist point of view, now you see an image with 28%, 29%, 22%. So when they average it, when there is heterogeneity, they will average it to the closest integer. For example, for this particular patient, it will be approximately 28%, which refers to a moderate steatosis. So this is the grading based on the cutoff. This cutoff only I said, this cutoff is different for 1.5 and 3 tests. Moving on to the liver content. Now if you see here, we are going to exploit, we are going to take T2 star relaxation. So what actually happens is, T2 star is the dephasing that you know. So R2 star, that is your relaxation time, will be the inversion of T2 star. And when you look at this graph, there is a drop in the signals. So the drop in the signal is proportional to the amount of iron content in the liver. So more of iron content, more of dephasing, more of signal loss. So that is what you are going to quantify. The planning is still the same, okay, and this is what it is. When you drop ROIs and calculate the average, this is a software that is provided by the vendor. See here, I put here as the first graph. You can see you have to feed in the value that you get, the average R2 star value, and choose the 3 Tesla. So automatically it tells you how much of iron is content is there, milligram per gram is there. So this is how you quantify iron, but you should know which MRI you're using. So based on that, the grading is, that is, you get the R2 star in hertz, the T2 star in milliseconds, and the iron content in milligrams per grams. So this is in the myocardium, yes, beta thalassemia patients, chemotherapy patients, where there is iron overload, every time a biopsy is not feasible. So these techniques are really very useful and valuable. So just to plan on the long axis, the short axis image is chosen, drop ROIs on the myocardium and quantify the same way. So two set of images are put. This is in a normal volunteer. The signal looks almost the same in all the 8 images with different echo times. Whereas the second set of image, you can see defacing, which is proportional to the amount of liver content in the myocardium, right? So again here, you quantify, you take the average of the T2 star value, feed it here, and you get the corresponding R2 star value and the iron content. Again, this is the grading of myocardium on a 3 Tesla MRI, and normal, mild to moderate. So you can see the time here, more than 172 will be a severe iron overload. This is in a 1.5 Tesla MRI Siemens machine. Again here there's color coding staging. These are the zoomed images of this. You can see as the T increases what are the values, and it gives the grading according to the colors. Green is normal, yellow is mild, moderate and severe iron overload. Moving on to the next technique, MR elastography, to evaluate the mechanical properties of tissue. So what is elasticity? The ability of a material to retain its original shape after it is being put into pressure, stretched or compressed. So we are going to evaluate the tissue stiffness here. Okay, for liver, in a healthy tissue and in a lesion or in pathologies, the stiffness increases. Okay, so this grading becomes really important to pick up pathologies. This is a schematic diagram. Look at this image. So what you see here is zone 4, the magnet room. So this is the technical room or the equipment room. A hard active driver is placed here. It is connected to the passive driver on the patient's abdomen through a waveguide. This waveguide is an entrance in the zone 4, through which, because I can show you here, this image, this active driver, it says unsafe. So it is outside zone 4 and it enters the zone 4 room through this waveguide. Okay. So what are we doing here? Basically, we are trying to apply mechanical waves that are generated by the pneumatic active driver, which is sent into the patient's liver or the abdomen by means of the passive driver. That passive driver transmits the mechanical wave in the form of vibrations, which cause displacements in the tissue at the micron level, and its wavelength, that is, it's in the horizontal plane, which is known as the shear waves. The wavelength of the shear waves are proportionate to the tissue thickness. So, as the tissue stiffness increases, when the stiffness is more, the waves travel faster. Okay? So this is what it is. So this is a pulse sequence. The parameter that you need to really look into is your driver frequency. On a standard across all equipments across the world, it is 60 Hertz, because for reproducibility and for validation purposes, it's always 60 Hertz. The driver amplitude is 70%. Of course, that is little variable between 70 to 100%. Okay, now the patient has to be in fasting. Okay, fasting, actually they say that in a patient with normal liver, the food intake does not alter the liver stiffness measurements. But in patients with fibrosis, they said that immediately after meal, there can be changes in the liver stiffness measurements. So better to insist on fasting. How do you position? This is where you place the passive driver on the patient's abdomen. Draw a line from the mid-clavicle, another line from the xiphisternum. So at the right upper quadrant of your abdomen, you need to place the driver and fasten it with an elastic band to maintain the contact. Okay, so this is how you do. Most important, optimize the parameters. So you use a phase contrast pulse sequence, and most important, your acquisition in breath hold has to be the end stage of expiration. So that is very, very important. So this is what it is. The waves are transmitted into the liver, and this is the wave image that you see. Okay. So the first set of images that you get will be a phase and magnitude image. Okay. And from these images you post-process and get grayscale and color scale elastograms and a wave image. Then you get another 4 set of images. 2 images without confidence map, 95% confidence map. This is with 95% confidence map. This is without 95% confidence map. Now why is this important? When you draw an ROI, you should see that it does not overlap the cross-hatched areas. If you see here, this cross-hatched area, so when your ROI is drawn, you should avoid such areas because there is poor wave intensity, distorted waves and hotspots are there. So all that will influence your value, so you should avoid that. So how do you do it? Before interpreting the images, you need to see if the images are correct, your technique is correct. So when you look at this first image, it's in a patient with a normal liver. See, the wave is very thin and it gets attenuated with signal loss as you move towards the center. Okay, the corresponding color scale image shows the least square is blue, violet to blue, which is normal. 1.9 kilopascals is the stiffness measurement. Whereas here, it's in a patient with fibrosis and you can see that the wave is thickened, unattenuated waves, and you can see the wave is not distorted here, there is no dark signals here, and you can see that green through red is a color code and a color elastogram. So once you know that these images is correct, then you start your measurements. So you should evaluate that you avoid the liver edges, large vessels, fissures, and then masses and the gallbladder fossa. On a wave image, you ensure that you look for wave distortion, avoid all that with low amplitude. And on the crosshatch regions, you avoid all that. Then you look at the, suppose the hotspots. What are the hotspots? They can be artifactual, they can be real. So it could be real if there are some masses or vessels, or it could be some artifacts. So you need to look at other grayscale images like a T2 weighted, even weighted images before you avoid the hotspots. So for example, this is your first set of magnitude image. You can either go for manual measurements or automated measurements. A freehand ROI tool will be easier. Just trace the areas where you need to quantify. Copy paste it on your wave image, then copy paste it onto your color and grayscale elastograms and then quantify. Now this area is different in different, right? So how are we going to calculate? So M represents your, so if you look at this formula, M represents the mean liver stiffness measurement and W represents the size of the ROI. So this is how you calculate. The numerator will be multiplication of the area with the measurement value, adding everything. The denominator will be just the sum of your areas. So in this particular patient, there's 2.5 kilopascals, which refers to, you can see here, it's a normal liver stiffness. So these are the different stages of liver fibrosis based on your LSM, that is your liver stiffness measurements. So similarly, pancreas measurements are also taken. We could also do it in the breast, we could do it in brain, lung. The technique little slightly varies. So pancreas also depends, it's not it's orthogonal plane. So you need to carefully place the driver, and your planning is very, very important. For the liver, see that you cover the major portion of the liver when you draw your ROI. So as technologists, first thing that you should see is whether the passive driver is fastened correctly onto the patient's abdomen. Checklist. Okay, whether the passive driver is applied during the end expiration, that is you acquire your image at the end expiration, whether the calibration scan is done, quality control is important, and whether you have included major portions of the liver, whether the driver amplitude is 60 Hertz or not, and the driver frequency. So that is very important. So quality control or quality evaluate, how do you look at the magnitude image? See, is there any signal void in the abdominal wall? Look if the sections are covered through the mid-liver. Is the overall signal intensity decreased or not? And are there any motion artifacts? In the wave image, look for good wave propagation. If it is diffuse or focal wave distortion, are there any low amplitude dark waves? Then you need to repeat it. Elastogram image on the grayscale and the color scale, you should see if the entire liver parenchyma is covered and whether there are any hotspots. Okay? So the take-home points are: familiarize yourself with the basic pulse sequences. Chemical shift imaging is exploiting the difference in the precision frequency of fat and water. See where you're working, 1.5 T MRI or 3 T MRI. You should be aware of the cross-sectional anatomy, familiarize yourself with that. And then ensure appropriate patient preparation, ensure checklist compliance, check for the patient's breath hold capacity, optimize the technical parameters and know how to do a post-processing, and quality control is definitely mandatory. Now, if you ask me whether you can do a elastogram with or without contrast, iron and fat quantification has to be done before contrast. But elastogram, literature says it does not, GBCA does not influence the measurements. But basically speaking, last week, one of our students tried a couple of sequences with and without contrast. And he says there's slight changes in the waveform, wave image, and in the measurements. So I think that is still under debate. We need to really evaluate that. Thank you all for the wonderful opportunity.